For the introduction, and let's start by analyzing some data regarding aging population that are showing an increase in the number of elderly people on a global scale, and this trend is projected to double by 2050. So accordingly, the growth of the elderly population proportionally affects the rise in the number of people affected by cognitive disorders. And at the same time, the number of elderly people who live independently tends to grow as well. And the most developed countries are those with the highest number of independent older-aged people. And the red bars in the figure indicate European countries ranging from 20 to 40% of over 65 years old living alone. And these percentages are projected to rise. So the problem is to lengthen the autonomy of these people and in their own home environment. So what's the aim of Ambient Assisted Living? Let's call it AAL, and primarily to support the elderly in independent, active, and healthy aging, particularly in those areas. And to this end, we know that the home environment plays a key role. Well, approaches to this problem have been evolving a long time, since the 80s and 90s, when home automation began to appear, and then it came to the building management system, which is a rule-based kind of building automation, and nevertheless, this kind of rules are determined a priori. And so the next step is defined by digital twins, which are an approach to complex system modeling that virtually emulates the real asset through a combination of agents, and that include the users as well. And the network, defined by both the agents and their mutual relationships, constitutes the building cognitive layer, which aims at predicting events and acting accordingly by means of customized services or applications. So the question is, how can digital twin support the ambient assisted living domain to allow an independent living person suffering from cognitive disorders to have an autonomous aging? This was our question and the purpose of this work, and we think the answer is by modeling agents and taking into account the user and its activities. So we were going to deal with multi-domain aspects, definitely not homogeneous from a modeling perspective. So we built a stratified layered system. This is the system we built, and we followed an approach that assigned each layer a specific function that sequentially feeds subsequent layers. And our architecture is based on 5 layers, the 4 blocks, and the transmission layer, which is represented by the arrows, and it indicates the information flow. So the system's objective is to recognize emergent scenarios, and therefore to detect the anomalous scenarios in the home environment, and make decisions autonomously to offer proper solution to the user. So from left to the right, the knowledge about the real environment develops. And starting from the computation required to manage the virtual real-time representation of the context that is included into the first 2 layers. And this representation consists of 2 main parts. The first one, the building objects that are represented as BIM information, which can also be associated with dynamic features such as sensor readings. And the second one, the user, and the virtual representation of the user is simplified through its posture, and we are going to call it a skeleton, that is acquired through a tracking algorithm that exploits 3D information from a LiDAR camera. Now, user activities must be recognized to create a complete representation of the scenario, and this task is performed within the 3rd layer. So this means that all the non-contextualized computational procedures employed to recognize actions and activities are included in the third layer. And to detect them, we followed an approach based on artificial neural networks. So moving forward, the next task consists in understanding the user's actions and activities and combine them with the other information coming from the context, and by means of this time contextualized computational procedures to the extent, of recognizing emergent scenarios. So, and then at this point, interacting with the user through a dialogue system. So let's go deeper by focusing on the virtual representation of the physical asset, exploiting BIM information for what concerns the environment and the skeleton for what concerns the user, as I said before. And but however, the skeleton itself is not enough to define a complete semantic of the user. So that's why we need also to understand and contextualize the activities of the user. Oh, sorry. Okay. To do that, we needed to stabilize our skeleton to have more confident data. So firstly, we discarded joints with confidence index value below the 10%. Instead, those with higher values of confidence go through a stabilization process based on autoregressive filters to ensure that the value at time t+1 did not deviate excessively from the previous one. So the value at time t, which would have otherwise resulted in the inconsistent human movements. You can see it to the left. Okay, now we have a clean skeleton. So among the activity recognition models available in the state of the art, we chose a neural network based on graph convolutional networks, which do not exploit images, the skeleton images, such as most of the convolutional neural networks, but exploits graphs containing the information about the joints of the skeleton. But due to some discrepancies between our skeleton and the one used by the NTU dataset on which the neural network model was pre-trained, we had to remap our skeleton to extract 25 joints instead of the 19 we had before. So at that point, we exported the remap, the skeleton joints information as a feature vector to feed the model. So this is the feature vector, and it is basically a spatial temporal tensor that includes the confident skeleton joints information, spatial coordinates at each frame time. And this data then feed the activity recognition model. And to the right, you can see are shown some examples. Okay, at this stage, we are able to recognize events happening within the scenario, the user skeleton, the position, and the activities. All these pieces of information, despite no longer being raw data, have limited value since they are not yet mutually combined. So therefore, now we are going to introduce a model to contextualize the information. The model is about Bayesian networks that are probabilistic models representing a set of variables and their conditional dependencies using graphs. And these networks are explicit model where each variable is associated to a node and has a clear semantic. So Bayesian network allowed us formalizing contextualized scenarios by eliciting causal dependencies among the nodes, and evidences within the scenarios and their relationships therefore define likely anomalous scenarios to be inferred by the model computing the conditional probabilities. Okay, this approach was applied to the detection of 4 types of anomalous scenarios, which are shown in the figure, and basically thus consist of dangerous or meaningless scenarios that may occur in AAL environments. So we formalized this object-oriented Bayesian network that consists of 4 submodules, and each module is dedicated to one of the 4 types of anomalous scenarios you have seen before. And the next slides will show the main three modules. Okay, the first one performs meaningless scenario detection, such as wearing clothes to go out without actually going out, and dangerous scenario detection, such as, for example, dropping something on the ground without picking it up and creating a possible fall hazard by tripping over it. And so in the figure, the evidences are on the top of the network, and moving downward, it infers situations, behaviors, feelings, and down the possible anomalous scenarios, and by pooling all the evidences. So these are the starting conditional probabilities of this module, and this is the example where we show the case where the user is getting ready to go out without, because evidences are given by the activity recognition module as putting on his shoes, hat and cap, hat and coat, sorry. But then the user doesn't not leave the house, actually, and might have forgotten, for example, cognitive disorders. So the system infers this anomalous scenario with high sensitivity. It's a little, but 88%, and will remind the user through the dialogue system that he was supposed to leave. The second module is about maintaining habits regarding meals, so preparing the meal and then eating, starting conditional probabilities. And the example that shows the case where the user has forgotten to prepare and have breakfast. Indeed, the system detects this unusual scenario and will interact with the user, reminding him or her to have breakfast. Okay, the third module that deals with environmental discomfort, relying not only on environmental information, but also on the user's own feelings. Conditional probabilities, and the example that shows the user is feeling cold because the window is open and the outdoor temperature is lower than the indoor one. So the system does not directly turn on the heating because it wouldn't make sense, but rather suggest the user closing the window first, and then at that point, should the user still feel cold, the heating system will be turned on. Okay, at that point, we developed the dialogue system. The dialogue system that, on the one hand, interprets the natural language as Alexa or Google Assistant, but without the necessity of hot phrase, the starting phrase. I don't know if you can, if it works, no? Okay, basically, you should have listened to me saying in Italian, I'm feeling cold, or I'm cold, and the system, you can see to the right, the system accurately converts my speech into text. And okay, on the other hand, it can transform the system cues in speech, and therefore allows a bidirectional, accessible and certified interaction with the user. So you cannot listen to the system answering me, but the system now is speaking and telling me, suggesting me to close the window before turning on the heating system, as the previous example. So conclusions, the results are prototypes of digital twin models supporting ambient assisted living scenarios developed and evaluated in its main functions, which are summarized here in this figure. And well, what about future developments? Firstly, should include the implementation of the system in a real environment with real data, and secondly, they will require to use larger activity data set to formalize more anomalous scenarios to be inferred by the system. Thank you.